At the heart of our solar system lies a yellow dwarf star known as the Sun. This hot, radiant ball of gas is the largest object in our solar system, with a diameter of about 1.4 million kilometers. It would take over 1 million Earths to match the Sun's volume, and more than 330,000 Earths to equal its mass. Hello, and welcome to Z. Please don't forget to subscribe and hit the bell icon. Such a massive object generates a significant gravitational force, attracting other massive objects toward it. The Sun's gravitational pull is so strong that it holds our entire solar system together, keeping every planet and asteroid in orbit around it. The Sun is also a vital energy source, and without it, life on Earth wouldn't exist. But what if one day the Sun disappeared and was replaced by one of the universe's most powerful and destructive objects, a black hole? These fascinating cosmic entities generate gravitational fields so intense that not even light can escape. There are various types of black holes, differing in mass, size, and origin. The most common are stellar black holes, formed when a massive star reaches the end of its life. Throughout its life cycle, a star may expand, cool, and change color until it exhausts its fuel. When this happens, particularly massive stars explode in spectacular cosmic events called supernovas. Sometimes a supernova leaves behind a stellar remnant that collapses into a tiny, extremely dense region known as a singularity. Surrounding the singularity is a spherical boundary called the event horizon, often referred to as the point of no return, because the escape velocity at this point equals the speed of light. Once an object crosses the event horizon, it falls towards the singularity and, as far as we know, never returns. Not all stars can become black holes, only those with sufficient mass can. Astronomers compare stars to our Sun to determine this. A star must be at least 8 times more massive than the Sun to go supernova, and at least 20 times more massive to form a black hole. Our Sun isn't massive enough to trigger such an explosion or collapse into a singularity, making the formation of a black hole at the center of our solar system extremely unlikely. Imagine a different scenario. Instead of a supernova creating a black hole, suppose our Sun suddenly vanished and an equally massive black hole took its place. Most black holes are much more massive than the Sun, but this hypothetical black hole would have just one solar mass, making it the smallest black hole ever discovered. Although the minimum mass for a black hole formed from a single star's evolution is around 2.5 to 3 solar masses, theoretically, a black hole with one solar mass could exist, though it's highly unlikely. There's ongoing debate about this, especially concerning the existence of primordial black holes, which may be much smaller. Black holes are significantly smaller in diameter than the stars that create them. For example, the black hole Cygnus X1 is 21 times more massive than the Sun, yet its event horizon is only about 124 kilometers in diameter, less than 1% of Earth's diameter. When a stellar black hole forms, the star's mass is condensed into a tiny singularity, making black holes some of the densest objects in the universe. A black hole with one solar mass would have an event horizon just 6 kilometers in diameter, over 2,100 times smaller than Earth, yet 330,000 times more massive. A black hole of this size would pose little direct threat to our solar system. Contrary to popular belief, black holes are not cosmic vacuum cleaners sucking in matter from across the universe. Objects close to a black hole's event horizon might experience extreme tidal forces, but at greater distances, a black hole's gravity is similar to that of other space objects. According to Newton's shell theorem, symmetrical spheres influence external objects as if all their mass were concentrated at one central point. This means that a black hole's gravitational effect on distant objects is similar to that of a star of equal mass. A black hole with one solar mass would barely alter our solar system structure. Each planet would continue orbiting this black hole at the same distances they do today. However, the disappearance of the Sun would have significant consequences for our solar system. The Sun emits a stream of charged particles called solar wind, extending beyond Pluto's orbit and creating a protective bubble known as the heliosphere. This region, dominated by the sun's magnetic field, shields our solar system from interstellar radiation like high-energy cosmic rays. Without the sun's protective influence, cosmic rays would enter our solar system more freely, increasing radiation levels on all planets, including Earth. These rays could also ionize planetary atmospheres, altering climates, weather patterns, and atmospheric chemistry. While our solar system might remain intact, losing the heliosphere would have long-term, far-reaching consequences for life on Earth. The sun not only shields us from interstellar radiation, but also provides light and heat through nuclear fusion. This process occurs when 4 hydrogen nuclei combine to form one helium nucleus, releasing vast amounts of energy in the form of electromagnetic waves. About 40 to 50% of solar radiation is visible light, which we perceive as warm sunlight, while most of the rest is infrared or ultraviolet radiation, invisible to our eyes. Unlike the sun, a black hole wouldn't emit visible light. If our sun were suddenly replaced by a black hole, it wouldn't illuminate our planet or sky. Instead, Earth and every other planet in our solar system would be plunged into perpetual darkness, though not immediately. Light from the sun takes about 8 minutes and 20 seconds to reach Earth, so the sun would blink out only after the last photons reached us. After that, a twilight glow would linger as light reflected off the moon and other planets. Once that fades, our planet would sink into darkness. Even the moon and other planets would vanish from view, leaving the distant stars as our only natural source of light. Without the sun, Earth would also experience a severe drop in temperature. The current average surface temperature is about 15 degrees Celsius, 59 degrees Fahrenheit, largely due to solar heat. Without the sun, temperatures would steadily decline. Our atmosphere might retain some heat, and we could gather some warmth from Earth's core, but these sources wouldn't sustain our climate for long. Tropical regions would become much colder, and bodies of water, including the ocean's surface, would freeze, covering much of our planet in ice. Only the deep sea might remain liquid, insulated by ice and warmed by geothermal heat. In such a dark, frozen world, life would struggle to survive. The loss of sunlight would trigger the most devastating extinction event in Earth's history. Photosynthetic plants couldn't produce food without sunlight, leading to the death of many species within days or weeks. Some parasitic plants might survive temporarily, but eventually, they'd succumb to cold and dehydration. Rich ecosystems like reefs and rainforests would collapse, starting from the bottom. Herbivores would starve as plant food dwindled, and predators would follow, leading to the extinction of most carnivores. A few species might survive by scavenging or living around deep-sea vents, but the vast majority of marine and terrestrial life would perish. Humans might be able to adapt. If the sun were replaced by a black hole, society might continue for a while, feeling like a long night. However, as the climate cooled, essential infrastructure would fail, especially in areas unprepared for severe cold. Pipelines would freeze and burst, power grids would collapse, leading to blackouts, and many would die in their homes. Food would become scarce as crops and animals died and supply chains broke down. Over time, our population would decline, but some might survive by using nuclear and geothermal energy for heat and power. We could build underground shelters to insulate against harsh surface conditions. With enough technology, humanity might endure for a while, but it would be our greatest challenge. Fortunately, the sun isn't massive enough to become a black hole, and it's not set to die anytime soon, at least not for another 5 billion years. So, while the idea of the sun vanishing is terrifying, there's no need to worry. Our sun will continue to shine for a long time. The sun is the lifeblood of our solar system, providing the essential energy required for life on Earth and driving the dynamics of planetary orbits. But what if, in an extraordinary twist of cosmic fate, the sun were replaced by a black hole of equivalent mass? This scenario, though purely hypothetical, offers a fascinating exploration of astrophysics, gravitation, and the delicate balance required for life as we know it. Gravitational effects. If the sun were replaced by a black hole of the same mass, the gravitational pull on the planets would remain unchanged. Black holes exert gravitational forces just like any other object of the same mass. Therefore, Earth and other planets would continue to orbit the black hole in the same manner they orbit the Sun. There would be no catastrophic change in the paths of the planets. They would remain stable in their orbits due to the conservation of angular momentum, impact on light and heat. While the gravitational effects would remain the same, the absence of sunlight would be catastrophic for life on Earth. The Sun provides the necessary heat and light to sustain ecosystems, drive weather patterns, and enable photosynthesis. A black hole does not emit light or heat in the same way. Consequently, the Earth would be plunged into darkness and extreme cold. The temperature on Earth would rapidly drop, leading to the freezing of surface water and the collapse of most forms of life. Within days to weeks, the planet would become a frozen, barren world. The role of Hawking radiation. Black holes emit Hawking radiation, a theoretical prediction by physicist Stephen Hawking. However, for a black hole with the mass of the Sun, this radiation would be incredibly weak and negligible compared to the energy output of the Sun. It would not provide any significant heat or light to offset the freezing conditions on Earth. Effects on human civilization. Human civilization is heavily reliant on solar energy, directly and indirectly. The sudden disappearance of sunlight would lead to the failure of agriculture, a collapse of the food chain, and the disruption of all solar-dependent technologies. The lack of sunlight would also halt solar power generation, further exacerbating the energy crisis. Societies would struggle to survive in the ensuing darkness and cold, relying on artificial light and heat sources, which would be insufficient for the long term. Thank you for watching and see you next time.